Hi, I'm Katrin Mester. I work for LKR, Leichtmetallkompetenzzentrum Ranshofen. I'm a senior research engineer here in the casting group, so I focus on aluminium alloy development. So main focus on aluminium alloys. And my background is material science. I did my PhD on aircraft aluminium alloys. We are in front of the SEM here, which is a major tool to characterize alloys. And so in the whole loop of characterization, we have the processing step. So here that would be high pressure die casting, HPDC. And when we come up with an alloy that has passed all the tests, so I think it's worthy to be produced via high pressure die casting, we have the cast parts, do some metallographic preparation, and then we have a look at it under the SEM. And especially when it comes to intermetallic phases, the morphology really counts. So depending on the generation of these intermetallic phases, we can somehow derive mechanical properties. And at the end of the day, mechanical properties are what we are looking into for material design and alloy development. Because if we have industrial applications, they don't necessarily care much about the microstructure, but they want a specific tensile strength, a specific corrosion behavior, and specific ductility, like for crash components, for example. So I look at the microstructure, and as soon as I can say that this might be a promising alloy, when I look at the structure, we select some certain alloys and we go to the next step, which would be tensile testing, which is a very good test to learn about mechanical properties. For example, we see a microstructure here. That's a high pressure die cast alloy. And so the really gray area here would be just the aluminium matrix. But then we have two different kinds of phases. We have this area here, which is a ternary eutecticum. You can tell from the color of what you see if you have light elements or heavy elements. So you can say now the darker, the lighter the element. So in that case, you have magnesium and silicon. And here in the brighter areas, you know that you have the major amount of impurity elements. So the troublemakers, iron, manganese, zinc, copper. From this picture, we would expect mechanical properties to be quite ideal. So this would be an example of a bad microstructure, so something that we are not looking forward to, because you can see that the structures that we have here are very, they're not combined. So we have large concentrations of the heavy elements in really large, so this is 15 micrometer scale. And as soon as you have a concentration of big phases, the mechanical properties will suffer. So once we've selected interesting alloys from the material properties and the microstructural characterization we just showed you, we go on for mechanical testing. So this one would be a tensile sample, easily explained. It goes into the machine, and then one of the stems pulls on one end, and at some specific strength and some specific elongation, the material ruptures. And these mechanical properties are very relevant for industrial applications, because you need to know how much energy the material can take in deformation, really, before it fails. So the ultimate goal is, of course, to have an alloy that has a maximum amount of scrap and a minimum amount of primary aluminium. And with this approach that we have, we can design an alloy with the highest amount of scrap. We know how the scrap and the special impurity elements are included in the microstructure and how the effect on mechanical properties is. And as soon as we understand what's really happening in the material, we can potentially even put more scrap into the alloy that the industry really needs.